When I was a kid, I was obsessed with bungee jumping. And the thing is, when I was 5, I thought, I'm doing this. So I go up to my bedroom where I have bunk beds, which is an important part of bungee jumping because you need something to jump off of. And I also needed bungee cords. So I looked through my drawers and I found suspenders, which are pretty much bungee cords, right? And I strapped one pair onto myself. Another pair I connected to the bunk bed and to myself. I got up top and I jumped. What you might expect is that these bungee cords were not quite strong enough to hold me up, and I smashed into the ground. To add to the embarrassment, those suspenders snapped back against my back, which probably hurt more than falling. Why did they snap back? Well, it's something called the restoring force. And when you stretch a bungee cord or suspenders, they want to pull back. This can lead to a repeated motion where you stretch it and it comes back, and you stretch it and it comes back. That repeated motion is called harmonic motion. And that's what we'll learn about in this lesson. Let's take a look. Let's begin by reviewing our lesson objectives. First, we'll examine the definition of harmonic motion. We'll figure out just what this thing is. Then we'll define frequency and amplitude, which are two important properties that describe harmonic motion. And lastly, we'll solve practice problems with harmonic motion so you get really good at this stuff. All right, first up, what in the world is harmonic motion? Basically, it's a back and forth motion that is repeated over and over again. So if you can think of a nice simple back and forth motion that's repeated over and over again, that's harmonic motion. We'll look at a ton of examples. This back and forth motion is due to what's called a restoring force, a force that always pushes it back towards the center. So remember, a restoring force is a force that drives an object back towards a central position. I think we need an example. Here you see a swing flying forward. It's at its fastest at the low point, and as it starts to go past that low point, past the center, the gravity begins to pull back on it, slowing it down. That's the restoring force in this case, the gravity. And eventually the swing reaches its high point and then turns around, going back towards the center. And the swing will do this over and over again. It's harmonic motion. How often it swings back and forth is called frequency. That's how quickly the back and forth motion is repeated. Let's take a look now at this clock. The pendulum swings back and forth at a constant rate. In fact, that's how it keeps time, by the constant rate of ticking. How often it swings back and forth is exactly what we mean by frequency. We typically measure that per second. So frequency is how quickly the back and forth motion is repeated, and most often measured in per second. Let's practice calculating frequency. A pendulum swings back and forth 127 times in 1.3 minutes. What is the frequency of its swings per second? Well, two very simple steps here. First, we want to know this per second, and our time is in minutes, so we need to convert time to seconds. Then we'll merely divide the number of oscillations by time to get how many happened per second. So first, let's convert time to seconds. We have 1.3 minutes, so we're going to multiply that by 60 seconds per 1 minute, and we'll get 78 seconds. Last step here, divide the oscillations by time. So the total oscillations, 127. The total time, 78 seconds. And we get then 1.6282 per second. What does that mean? Well, it means that about 1.6 times every second, this pendulum swings. Let's round that to sig figs. There's 2 sig figs and 1.3 minutes, so we'll round this to 2 sig figs. Next up, just a unit we often use instead of per second is hertz, named after a famous scientist. And we'll abbreviate that Hz. So remember that hertz is the unit for frequency, which means per second. If I say hertz or per second, they mean exactly the same thing. Last property of harmonic motion for you to know is the amplitude. It's basically the size of the back and forth motion. Now, a nerdier way to say size is the magnitude of the back and forth motion, but we mean the same thing here, basically how big it is. For example, The jumping up and down on a trampoline can also be harmonic motion. The child falls and rises repeatedly, with gravity pulling her down and the trampoline forcing her back up. The height of her bounces, that's sort of what we're after with amplitude. How big those bounces are. Now, here's the thing about amplitude. It's the magnitude of the back and forth motion, very specifically measured from the center of oscillation. What do we mean by that? Well, let's look at another example of harmonic motion, a block on a spring. So here we have a spring attached to a block, and right now the spring is compressed. And that blue arrow is telling us it's about to travel downward because the spring's compressed. So the spring expands as it travels downward. But if you think about this, that would mean that the block is now moving pretty fast. So even though the spring is at a nice equilibrium position, it's going to keep traveling past that and start to stretch the spring out. As the spring gets stretched, it wants to pull back towards the center. You can see here that the stretching and compression of the spring is the restoring force in this case. So now our spring begins to compress again, and then it reaches its equilibrium position with some velocity, and so it travels past it. And over again. This is harmonic motion, and now we're in a good spot to visualize the amplitude. Remember, that's the magnitude of the back and forth motion measured from the center of the oscillation. What do we mean by the center? Well, that dashed line is the center point for our oscillation, 0 inches. And the blocks get about 2 inches above that, and about 2 inches below that. And so that means our amplitude is 2 inches. Now let's give you a chance to practice estimating amplitude. Estimate amplitude of the following pendulum swing. So here, try to pick the center and then see how many inches does it go to the right and to the left of that swing. Were you able to do it? Well, the center of the swinging is right about there, about 4 inches. And that means that it goes from 4 to 8, that's about 4 inches, and also from 0 to 4. That's about 4 inches. So measuring the distance from the center of that swing, we get an amplitude of 4 inches. Okay, last chance for you to practice. Which of the following are examples of harmonic motion? Pause the video and give this a try. Well, A is a ball rolls down a set of stairs. That's not harmonic. It might bounce down repeatedly, but it's not staying in the same spot. It's moving down the steps. A chandelier swings forwards and backwards. That is harmonic, a nice repeated motion where gravity is acting as the restoring force. A car races around a curve. Not harmonic motion, nothing repeating there. A spring expands and contracts. That's harmonic. It's going to expand, contract, repeating that motion over and over again. Lastly, an ocean swell rises and falls. Here again, we have a nice repeated motion. We're thinking about specifically an ocean wave in the middle of the ocean. And there, the water rises and falls in harmonic motion. Let's review what we've learned. First, we examined the definition of harmonic motion, where we saw it's a simple repeated back and forth motion. Then we defined frequency, which is how often that back and forth motion happens, and amplitude, which is how big that back and forth motion is. And lastly, we solved practice problems with harmonic motion. Hey!